morning. Last time we have introduced a concept called piecewise interpolation, and why it is required, or in other words, why it is so important. This is because of the presence of a round of error is a very in a very huge manner in when you deal with a high degree polynomial, or you can say you derive the high degree interpolating polynomial. Okay, and what was the idea is for piecewise interpolation. So you have the given data, and what you will do is you are getting now creating blocks. So first 4 points, then and then you have x3 to x6 is another 4 points, and so on. So you will divide into blocks, and then for each block you will have a here in this case you will get a cubic polynomial, interpolating polynomial of degree less than or equal to 3. And so to make so to keep the continuity here, then we have started from x3 onwards. Okay, right. So let's go into more detail about it. Okay, right. So we are first we will look at the piecewise linear interpolating polynomials. So then means like this heading is here piecewise linear polynomial or interpolating polynomial. Interpolating polynomial. So we will look into the detail of this interpolating polynomial, and then we will look for quadratic interpolating polynomial, and then at the end we will try to address the cubic interpolating polynomial. Okay, and then how it will affect our previous notion, what we have got from for defining higher order or higher degree interpolating polynomials, that we also try to address here. So if you so we have the following equations. So first thing is the function f is a real valued function, and which is defined from closed interval ab to r. Now you take n belongs to natural number. So n belongs to natural number, and and we are going for equispaced data. Okay, so we are not going for means like not non-equally spaced. So we are going to with equidistant data. So we are deciding what is the distance between any two consecutive points is h equals to, that is b minus a by n. And then we have the notations for this xi's, that is given by a plus ih. So I is running from 0, 1, 2, and so on n. 1, 2, n. So these notations we will carry forward. Okay, and we first look at the linear interpolating polynomial in a certain block. Okay, and then we will try to cover the whole interval. Okay, so this is let's say x0 and x1. So for linear interpolating polynomial you require 2 points, and so x0 comma x1 belongs to, let's say, closed interval ab. Then you have, if you recall, what will be the interpolating polynomial of degree less than or equals to 1. You can just go back and look at the definition of Newton's interpolating polynomial. So f at x0, that's very straightforward. So plus the first divided difference of x0 x1 times x minus x0. So P1 is a polynomial of degree less than or equal to 1. and with the property that P1 of x naught is equals to f of x naught. So these are the interpolating conditions it needs to be satisfied. So P1 at x1 also is going to be f of x1. Okay, and if you also recall the error here. So if I recall, the error is at any point x between x0 to x1, you can have this f of x minus p1 of x. So we have also seen that in terms of divided differences. When you are not aware that whether the function is differentiable or not, or how many times it's differentiable. So it is indeed it was the second derivative, right? So but that if we are not known that what whether the function is differentiable or how many times it is differentiable. Okay, so then we can leave it with this divided difference x naught comma x1 comma x time x minus x naught into x minus x1. So for linear interpolating polynomials, so this you can recall from the previous session, okay, that where we have defined the Newton's interpolating polynomial. Now let's look at the this interpolating points. So interpolation points x0 and x1 and so on. So here, once you look at here, so h equals to b minus a by n, and x0, x1, x2, xn are the interpolation points. Okay, so far, let's say these are means like you have the this. Let's say this is the point, and this is the point B. Okay, and this is x naught and this is xn. That's very clear. Okay, now what else is, so you have the here, so you have this is x1, x2, x3 and so on. So this is, let's say, xn minus 1. Now suppose so there are two things, whether you choose these points itself as interpolation points, or so for linear interpolation you can choose any 2 points between this interval for getting the linear interpolation. Like here as well, you can choose any 2 points here, any 2 points here, and any 2 points here. But what will be the loss here? So it's the corresponding values. Let's say this is the value. These values are, let's say this is the corresponding value here. Okay, for this case, let's say this is there, and let's say this is the value corresponding. So when linear interpolation means you are joining these 2 points by a straight line. Okay, for linear interpolation at these values, so you are joining these 2. So when you choose 2 points in between these things, okay, so like x0 to x1, any 2 points you choose, okay, means not the boundary point. If you're not choosing these boundary points as the interpolation point, instead that you are choosing any interior point, any 2 points. So there you, so like here also if you join these 2 points with this, and what you will observe from here is the continuity loss. So at the points, so this, see, you can see this is here is continuity lost. Okay, so means the continuity will be lost here. So if you choose this x instead of x0, x1, x2 and so on, xn minus 1 as an interpolation point, if you don't choose this, and if you choose any 2 interior point here, so there is a loss of continuity itself. Okay, so still you have a piecewise linear interpolation there, but continuity also lost. Okay, now if you wish to preserve this continuity, so what you have alternate is you divide the interval like this: a x0 x1, x2, x3 and so on. This is xn minus 1 and this is xn, that is b. So if you wish to preserve the continuity, you need to choose this x1, x2, and so on. These all are itself the other interpolation points. So between these two, x0, x1, so x0 and x1 have been chosen as interpolation points. So what you will have is, let's say the value at this is this, and let's say this is there, and the value at this is here. Let's say this is the value here, and so on. So let's say this is there. So once you join by the straight line these 2 points, so you will get the continuity here. So continuity preserved, as well as piecewise structure is also preserved. But what will be the loss here now? So earlier interpolating polynomials, when you are deciding, so when you have the interpolating polynomial, higher degree interpolating polynomial, they are C infinity functions, means like you can differentiate as many times you wish. But here, see, when you talk about in between any point here, when you talk about any point here, interior point of x0 to x1, it is infinitely time differentiable. But when you talk about these as this here, okay, so these are the points where you are lose the differentiability. Okay, so you will lose the differentiability. So continuity preserved here and the differentiability lose. So overall, it is continuous function only. You mean if you define the function interpolating function, they like in linear with the piecewise structure. Okay, so with the piecewise structure, if you define, then overall it will only preserve the continuity. So it is not even first time differentiable. Okay, so let's what will happen if you wish to still preserve the one time differentiability? What will happen? You will get the single polynomial. So let's say, so let me give you the structure here. When you have you assume that the continuity and differentiability both is there. Okay, right. So let's say these are the let's say one interpolating polynomial is, let's say, p naught of x is equals to a naught plus a1 of x. Now see, if you go back and check, so it is the matter of joining two polynomials, right? So joining two linear, so how it will behave if you wish to include the differentiability condition. So let's see. So let's say another one polynomial is here. This is this, and let's say x belongs to, let's define the interval 0 to 1, and the another polynomial, let's say q naught of x, that is equals to b naught plus b1 of x, with x belongs to 1 to 2. Right. So you see, at present here you are talking about the 0, 1, and 2. Right. So now, if you don't impose anything, so at starting the starting phase here, you have 4 arbitrary constants. So degree of freedom is 4 here. Okay. Now, if you impose the continuity condition, so if you don't want continuity condition, you can fix any a naught a1 and b naught b1, depends. Okay. And then if you wish to impose the continuity condition, so if you imposing, let's say, a continuity condition. So imposing continuity condition at where you have to look at is at x equals to 1. So at only the partition point you need to look at, because in anywhere before 1 and after 1, okay, the function is continuous only. Okay, so at x equals to 1. So what that mean is p naught of 1 must be equals to q naught of 1. See, limit exists and all that you can take care of. So p naught of 1 equals to a q naught of 1. So if you impose this condition, what you will have is a naught plus a1 is equals to b naught plus b1. Now what will happen here? So once you impose this continuity condition, so what you will get is, so from here b1 equals to a naught plus a1 minus b naught. So only 3 arbitrary constants now. So 1 degree of freedom is gone. Okay, now if you further impose the smoothness here, so first time differentiability. Okay, so one time, so you have let's say imposing differentiability condition at x equals to 1. What that mean is the p naught of dash 1 dash different dash stands for the derivative, so q naught dash 1. So now if you perform the derivative of the above linear polynomial, that will give you a1 equals to b1. So with this condition, so a1 equals to b1, and here from here, so these are two conditions now. So from this, so continuity and differentiability both are there. So a1 equals to b1, that will implies equals to b0. And what it gives you? The single polynomial. So, right? So single polynomial. So once you are imposing more conditions, then you will lose the some here degree of freedom. Now, in the case of linear interpolating polynomials, what you will get is if you impose a differentiability condition also, or if you demand that the function needs to be differentiable at the partition point here, then you will get only single polynomial. There is no other polynomial available. Okay, right. So means, so if you wish to retain the piecewise structure, okay, so you can only impose the continuity condition at x equals to 1. So still the piecewise structure will remain there. Okay, so there is a then means you can only demand at most some up to some level only. Okay, based on the your requirement. Okay, right. So similarly, you can show for the quadratic polynomial. Okay, so this is about the linear polynomials. Okay, similarly, you can talk about the quadratic polynomials. So if you have quadratic polynomials, so if you look at the quadratic polynomials, is let's say you have this p naught of x is equals to a naught plus a1x plus a2x square, where x belongs to 0 to 1, and q naught of x is equals to b naught plus b1x plus b2x square, with x belongs to 1 to 2. So if you use, so you are imposing, so if you impose the condition, continuity condition, p naught 1 equals to q naught of 1, you will lose the degree of freedom here. What degree of freedom? So this will implies a naught plus a1 plus a2 must be equals to b naught plus b1 plus b2. Now, if you impose the condition, another condition, one time differentiability. So P naught of dash 1 is equals to Q naught of dash 1. So that will give you that B1, if you can verify that 2A2 is equals to, this is A1 plus 2A2 equals to B1 plus 2 times B2. Now, still you can preserve the piecewise structure here, because here still degree of freedom is there. So here and here, these two conditions will not it will not make it reduce to single polynomials. But if you impose one more condition, so p naught double dash at once, you want two time derivative exist and they are equal. So then this will be implies 2a2 is equals to 2b2. And if you go back and check all, so this will reduce to the single polynomial. The only possibility is single polynomial. So when you talk about the piecewise quadratic polynomial, okay, then you can, if you wish to retain the piecewise structure, So what you can demand at the most is overall one-time differentiability, is continuously differentiable. Okay, not the derivative is also differentiable. So okay, so this is here. I hope this will be clear now. Similarly, for cubic polynomials, you can also ask at the most two-time differentiability if you wish to retain the piecewise structure. Now let's come back to here our piecewise linear interpolating polynomials now. Okay, and let's see how it will be working. Okay, so we can demand at the most overall continuity of the piecewise linear interpolating polynomial. Okay, and we can define, so here so we are carrying forward the notations now: x naught, x1, x2, xn, and h equals to b minus a by n. And so okay, so we are going with now piecewise linear interpolating polynomial. So you have the f from a, b to r, so real valued function. Okay, and over x naught to xn, x1, you have the structure, right? So you have ab, and let's say n belongs to, I'm just defining, h equals to b minus a by n, and xi is equals to a plus ih, where I is running from 0, 1, 2, and so on till n. Okay, and we are choosing this x naught, x1, x2, xn are the interpolation points here. So we want continuity, function is continuous. Okay, and so what you can have is here is in case when you talk about the interval, let's say xi to xi plus 1. So there are n sub-intervals. So over this interval, you can define, so we wish the function g, you can say, okay, so we, because of n, it depends on n as well. So what we wish is to define a function gn such that restriction, so gn is gn restricted on xi to xi plus 1, so interpolating polynomial restricted on to xi to xi plus 1 is a polynomial of degree less than equals to 1. So how will you define is, so gn of x over this interval x to xi plus 1, that is by using the Newton's interpolating polynomial, that is equals to what? F of xi plus f of xi comma xi plus 1 time x minus xi, for x belongs to xi to xi plus 1. So this is the very straightforward. So gn is a function, is an interpolating function. Okay, and what we require is gn is continuous. So gn is from closed interval ab to r. So you can vary, I is running from 0 to n minus 1 here. Okay, so gn is so ab you have subdivided into n equal n sub intervals, and on each restricted interval gn is a polynomial of degree less than or equals to 1. And how will you define this gn is by using the, again, this the Newton's interpolating polynomial, by using this f of xi plus, so you are using these 2 points xi and xi plus 1. Okay, now, and what we require is gn is continuous. So when you are taking these interpolation points, so just the continuity preserved. So that we have just now seen. Okay, right. So this is going to be piecewise linear interpolating polynomial. So let's see the error term here. Okay, what will be the possible error here? Okay, right. So let's see the error now in this. So now let's look at the error in piecewise. I'm talking about piecewise linear interpolating polynomial. So we are talking about on the interval xi to xi plus 1. Okay, on xi to xi plus 1. So every interval you are defining the error. So what was there is, if you recall, what was that is f of x minus gn of x on this interval we are talking. So that is equals to f of xi comma xi plus 1 comma x time x minus xi into x minus xi plus 1. If you recall. Now, what we assume is we have the assumption now. Okay, so let's assumption here is, so beforehand, what we have the assumption here is f is 2-time differentiable, at least. Okay, 2-time differentiable. Okay, so let's make this assumption here. Then if you use the application of, if you use the rules theorem, then you will have there exists, so this will be, so above here there exists is some c such that this f double dash of cx by 2 factorial time x minus xi time x minus xi plus 1. Okay, so that we have already worked over it. So okay, so application of Rolle's theorem will gives you this. Now what you wish to have is, you wish to this error. Okay, so if you wish to bound this error means I'm going to take the infinity norm on both sides. So infinity norm is maximum of this here over the interval xi to xi plus 1. Then similarly maximum of on this side. Okay, so if you apply the infinity norm here, so this will imply, so maximum of x belongs to, I'm having xi to xi plus 1 mod of f of x minus gn of x is going to be less than also equals to maximum of this equals to 1 by 2 time maximum over x belongs to xi plus 1. So if you the maximum over this side, so cx belongs to the interval xi to xi plus 1. So I'm taking the maximum over this interval, so it's going to be certainly because cx is any random, so I'm going to take it is less than equals to maximum of f second derivative at x with the magnitude time maximum of that mod of x minus xi time x minus xi plus 1 and x belongs to xi plus 1. Okay, so this is going to be, so now see this, I see at the right side I wish to get rid of this i's. Okay, so what I can do, so I can, instead of performing the maximum of second derivative here, so what you require to attain the maximum here is continuity of f second derivative. So assumption f is 2-time differentiable and f double dash is continuous. So this is also required to make that the maximum does exist. Okay, on the closed interval. So now with this is going to be less than equals to, so I'm replacing the this maximum by norm infinity. We know that that's this definition by 2. Now what about this second quantity here? So in the product term, that we have already seen that this this product will be maximum at the midpoint of the interval, and what we have is this is going to be less than equal to, you have this is going to be at midpoint of the interval. So we have already checked with this. So this is going to be xi plus 1 minus xi by 2, the maximum value time here. Okay, so that is going to be the final xi plus 1 minus xi. If you evaluate that at x equal to xi plus 1, xi x plus xi plus 1 by 2. Okay, so that we have already shown. So xi plus 1 minus xi is h. So this is going to be h square by 4. So you have norm of f double dash infinity norm by 8. Okay. Now what is h? H is b minus a by n. So so if you note that is equals to b minus a by n. So a and b remain fixed. So when you vary n tends to infinity, this tends to 0. As n tends to infinity. That's the right hand side behavior. Okay. Now, so since this right side here, so since the right side in this expression are now completely independent of the left side, so you can still perform the maximum over I on the left side, and this remains still valid. So this implies, so if you take maximum over you can say 0 less than equals to I less than equals to n, and this maximum over, you can have x belongs to xi plus 1 time mod of f of x minus gn of x. This is going to be less than equals to the infinity norm of this by 2 by 8 h square. That still remains true. And what the left side is, this is going to be norm of f minus gn infinity norm is going to be less than equals to norm of f double dash infinity by 8 h square, and which tends to 0. So which tends to 0 as n tends to infinity. Okay, so this way means, so we have also talked about now error. Okay, so it's now very clear that piecewise linear interpolation, how it will behave. It will behave in the similar way. So error bound is still remain the same only. We have that. So you have to, so you can work with the examples. Okay, you can work with the example, and you can you require what 2 points only, A and B. So if I want to deliver one example here, so construct piecewise linear interpolating polynomial for the given given data, you can see. So you have the data now. Let's say this is x and this is f value. Let's say this is x value is minus 1, 0, 1, and 2. Let's say this is there. Okay, and let's say f of x is means like, let's say f is square root of x. So okay, no, so we are having square root of x. F, we require 2-time differentiability, so we can't define on 0, 1, 2. So what we can do here is we have is let's say 1, 2, and let's say 3. Okay, and now this is at 1 is 1, at 2 square root of 2 is 1.414, right? What will be the square root of 3 is also 1.732 something. Okay, and right. So now if you are you require, so you are going to define, so x0 x1 then x1 x2, these are two intervals. Okay, now what is be the here is say 0.414, this first divided difference. Okay, and what you will have is going to be, it is 0.318. So you require only first divided difference here, right? So what you will have is, so Gn, so here n is 2 only, right? So G1 you can say is, or G2, n is 2. So number of subintervals are 2. So G2 restricted on 1, 2. You have at x is equals to, you have f at 1 plus the divided difference at 1 comma 2 times x minus 1. So f at 1 comma 2 is given by this. So this is going to be 1 plus 1.414 times x minus 1. Now similarly G2 is restricted to 2 to 3. Is going to be f at 2, that is 1.414 plus f 2 comma 3 times x minus 2. So that is equals to 1.414 plus f23 is a point. This is going to be here, f12 is 0.414 here, and this is 0.318 times x minus 2. Right. Now what will be the, so you can check the continuity is preserved, right? Because G2 at 2 is 1.414 for this case, 2 to 3, and for this case at 2, that is 2 minus 1, so 1.414. So continuity preserved here. Okay, right. Now let's see that how, so if we decided the desired number of accuracy, so how many number of sub intervals we require. So let's ask the reverse question now. Okay, so let's answer this question now. Okay, so we are going to work with the same problem here. So let's have this following example. So let's have f of x equals to square root of x, and x belongs to 1 comma 2. So it is infinitely time differentiable indeed. Okay, and if you recall the piecewise linear interpolating error, what will be is norm of f minus gn infinity is going to be less than equals to norm of second derivative infinity by 8 h square. And what is h here is h equals to b minus a by n. So what is in this case, b minus a is 2 minus 1 by n, that is equals to 1 by n. Okay, now what we require is f double dash infinity norm. So what here is, so from the definition of function, so what is f dash is 1 by 2 root x. What is f double dash? If you differentiate, that is going to be minus 1 by 4 x to the power 3 by 2. Now this implies, so you are talking about x belongs to 1 to 2, and now you see in this interval 1 by x here, so it is a decreasing function. So maximum occur will be the left end of the point. So in the absolute sense we are talking, so we are having, so what is the norm f double dash infinity norm is equals to maximum of x belongs to 1 comma 2 mod of f double dash of x. So magnitude is 1 by 4 x to the power 3 by 2 over this interval at x equals to 1, that will give you the maximum, that is equals to 1 by 4. So now from here now, so this will imply norm of f minus gn infinity norm is going to be less than equals to, so 1 by 4 is there, right? Norm infinity is 1 by 4, so h square by 32. And let's say this we wish is less than 10 to the power minus 6. Let's see, this is going to be less than 10 to the power minus 6. Now you need to determine from what value of n, or how many number of subintervals required. So if you have, this implies h square is greater than, this is if and only when, provided so h square is greater than or h square is less than is 10 to the power minus 6 times 32. Now what is h is 1 by n. So if you so this is give you, this will imply 1 by n square is less than 10 to the power minus 6 times 32. So this will be possible provided n square is greater than 10 to the power 6 by 32. And now if you see the value of n, so let's say n equals to, then here n equals to 200 will work. If you work out, n equals to 200 will work. So how many number of subintervals require is 200. Okay, so that is a huge. Now what we can do here, so we can improvise this by going for, we are expecting that if we go for quadratic piecewise means like piecewise quadratic interpolating polynomials, then whether it will be reduced. So we are expecting that it should be. Okay, so let's go for it and let's see and whether it will change dramatically or is like what will happen in the case of quadratic interpolating polynomial. Okay, I'm just now going to talk about some space. Okay, so if you define let's say space Xn. So Xn is the space. So how this is reduced is Xn is the space where F. So we are going to. So we are going with the now general case. Let's say first defining for, let's say some use the notations. So we are using that k is greater than equals to 1. Okay, so let's say k is greater than equals to 1. And you are so we have that f is a real valued function, av to r is a real valued function. Okay, now so let's say xn is the space of containing interpolating polynomials, a real valued function ab, real valued function, such that G restricted on the interval xi to xi plus 1. So uniform partition we are taking is a polynomial of degree less than or equals to k. So if k is equals to 1, you are talking about the linear polynomial. It means polynomial of degree less than equals to 1. If you take k equals to 2, it's a polynomial of degree less than equals to 2 and so on. Then what will be the dimension of xn? So far we have not assumed any condition on G, even the continuity also. Okay, so the dimension of xn, what will be the this space dimension is, so each polynomial have k plus 1 are arbitrary member, right? A naught to ak. So this n, they are n in number, so that is going to be n into k plus 1. So that is, you can say also in other words, degree of freedom. Okay, now if you define that, if you let's say G belongs to the set of all continuous functions, real valued functions, means you are giving the continuity, you are imposing the continuity condition. In G restricted to xi plus 1 is a polynomial of degree less than equals to k. Then what will be the dimension of xn? So a dimension of yn here. So you have compromised somewhere. So you are taking all the points are interpolating points for itself. Okay. So what is happening is you are putting n minus 1 conditions here, right? P at 0, P at 1, P naught at 1 is equals to Q naught of 1, if you recall from the previous lectures. Okay. So if I want to define here, so let me have here. So you continuity conditions at the in between interior points. So a equals this a b, and this is x naught, x1, x2, and so on xn minus 1. So you are defining the conditions at these points. So n minus 1 numbers. So n minus 1 conditions are there, and what will be lost here is, so n into k plus 1 was the earlier one, minus one condition at each at those n minus 1 points. So that is going to be reduced n minus 1 in number. Okay, so then you will have, if you simplify it, this is nk plus n minus n and plus 1, so nk plus 1. Now if you demand the c1 here, so another space Zn is equals to g belongs to c1 ab. If you demand this, then what will happen? So you are again one more conditions you are putting, means like two conditions at each point. So at this point x1 you require the one-time differentiability and continuity. Okay, so what will be the dimension here is, like you can this will be dimension of Zn will be n into k plus 1 minus 2 time n minus 1. So, right, 2 time n minus 1 conditions will reduce. Okay, so this is going to be something like nk plus n minus 2, so minus n plus 2. Okay, and so on. So similar, you can go with the till the ck. Ck is, so c1, c2 is 2 time differentiable. 3 time continuously differentiable means C3, and so on. So let's look at the quadratic piecewise quadratic interpolating polynomial. Okay, and we are demanding now the piecewise structure for quadratic interpolation. Okay, right. So we can demand at most C1 here. So over R we can demand only C1, means continuously differentiable. So first time differentiability, and it is continuous. Okay, at the interpolation points. Now, so if so we are going with now we wish to define piecewise quadratic interpolating polynomial. So we are carrying forward the notations as follows. So f from closed interval ab to r, real valued. Okay, and you have n belongs to natural number. Okay, and you have this xi is equals to a plus ih. What is h is b minus a by n. Okay, right. So later on we will make assumption on f for talking about the error or bounding the error. Now what you can do, so for piecewise, so for quadratic interpolating polynomial, so like in linear interpolating polynomial, you require the 2 interpolation point. Okay, so in quadratic interpolating polynomial you require 3 at the starting. So if you choose the x0, x1, okay, then what will be the favorable here is the midpoint of the interval. Okay, so so you have 3 points now, a plus b by 2, and b. Then we will generalize to further. Okay, so you choose the midpoint of the interval, so x0 to xn. So if you go with the interval, let's say x0 to x1, then we are going to use the points x0 plus x1 by 2, and then x1 as the these are the points. So see, we don't need to have this x0 plus x1 by 2 as the interpolation point, because we are ending here. So we are going to join the another polynomial by at this end, x1. Okay, However, when you go with the data, since these values are not available, so what you can do is you can take first three, then next, and so on, like in continuity manner. Okay, so theoretically, this is the here. Okay, and when you have the values, corresponding values here, f at x naught and f at x naught plus x1 by 2 and f at x1, if you know. Okay, so in practice, what you will take is x, x1, x2. Okay, so I hope that is very clear. Then what will be if I to write gn restricted at, you can say, I to xi plus 1. The quadratic interpolating polynomial, like we have done previously, that will be f at xi plus first divided difference xi comma xi plus xi plus 1 by 2 time x minus xi plus second divided difference, that f of xi comma xi plus xi plus 1 by 2 comma xi plus 1 time x minus xi into x minus xi plus xi plus 1 by 2. So that is GN, that interpolating polynomial on the interval this. So you are using the similar concept what we have done for Newton's interpolating polynomial. Okay, and these divided differences can be get from the table, like we have done for the previous example. Okay, we are going back with that again for this problem as well. Okay, so now, so we have this is, so your I is running from 0, 1, 2, and so on n minus 1 till n minus 1, because we are having I plus 1 here. Okay, so you have the Gn. Now, since these are the these xi to xi plus 1 are the interpolation points, and you are joining the points here itself, so continuity remains preserved. Okay, and also differentiability is also there. One-time differentiability is also there. Okay, because it's a polynomial, so it's a differentiable. So what you need to worry is at the endpoint. Okay, so those things are also can be okay because of the nature of this polynomial, that you can verify that whether a Gn is differentiable at xi plus 1 and xi or xi minus 1. So this is what here is. So you have the interval is xi minus 1, xi, and xi plus 1. Okay, so what you require to verify now is, so if you say this is the polynomial pi, what is that? Pi is Gn restricted over the interval xi to xi plus 1. Is a polynomial of degree less than equals to 2. And you can say this here is the polynomial, you can have the notation pi. And you can verify that pi at xi plus is equals to at derivative pi minus 1 xi minus. Once you verify this at derivative, then you are through that. This preserves the differentiability as well. Okay, so that I can leave it as an exercise for you, that you should verify. Okay, that you should verify. Right, because we wish to preserve the differentiability. Okay, so left hand derivative must be equals to right hand derivative. So here, so only you can talk about pi as pi dash xi plus and pi minus 1 dash xi minus 1 there, and if they are equal, so that is differentiability is true. Okay, so now what we can talk about is error term. Error term in quadratic interpolating polynomial, what will be is given by over the interval. So we want to get the error on, you have xi to xi plus 1. So again, by the similar process, so you have f of x minus, you have if you recall, that is gn gn of x over the interval. This is equals to f of xi comma xi plus 1 by 2 comma xi plus 1 comma x time x minus xi into x minus xi plus 1 by 2 time x minus xi plus 1. Now you need to assume that f is 3 times differentiable and the third derivative is continuous. So that's the assumption is required. So assumption is f is 3 times differentiable and f third derivative is continuous. So once you have it, okay, once you have this will imply that on the interval f of x minus gn of x on the interval xi to xi plus 1, that is equals to, by again application of Rolle's theorem, says that f third derivative at some c lies between xi to xi plus 1 by 3 factorial time wx. So what is wx? So wx over the interval xi to xi plus 1 here. So x minus xi into x minus xi plus 1 by 2 times x minus x. Now again you repeat the same thing what you have done for linear interpolating polynomials. So this will imply that you can say verify. It's very easy. Similar steps you have to follow. That norm of f minus gn infinity norm is going to be less than equals to norm of third derivative infinity norm by 3 factorial the infinity norm of w. Now also what we have, so we have also seen in when we are dealing with the quadratic interpolating polynomial error term and equispace data is there, that there we have shown that in that lecture that norm of w infinity norm is going to be given by over this interval 2 by 3 root 3 time xi, in this case xi plus 1 minus xi by 2 cube. That you can verify. Again, so what you have to look for, so see, this is the mod of x minus xi into x minus xi plus 1 by 2 times x minus xi. So it's a cubic polynomial. So for looking at the infinity norm, you have to look at the boundary points and the points where the derivative does not exist and the points where the derivative vanishes. So those points you collect and make a table of all possible values in magnitude sense again. I'm talking about. So in magnitude sense, you collect all the possible those numbers at those critical points that we are saying as those are critical points. And then the maximum over this will give you the infinity norm for this W. So once you have 8, so this is going to be less than equals to, okay, so then you can plug this here. So that is equals to norm of, so third derivative infinity norm. So 3 factorial is 6, so 2 will get cancelled. So 9 root 3 time, so 2 cubed is 8, so 72 root 3 time xi plus 1 minus xi is h cube. Yes, so by looking at the error term, so we can expect that is h cube here on the right side. So this is which is faster than the h square. So in the linear case, what we were having is h cube, h square, right? So that so the h cube will be the much faster than the h square. Right. So now let's work with the same example now. Okay, and then we wish to desire the same accuracy. So we have f of x equals to square root of x. X belongs to closed interval 1 to 2. Okay, h is equals to b minus a by n, so 1 by n. We wish to decide what is the step size we require to take so that the error remain less than 10 to the power minus 6. So and we wish to go for quadratic interpolating polynomial. So for the case quadratic interpolating polynomial, what you have is you need to determine third derivative infinity norm. So from here, what is f dash was is, if you recall, 1 by 2 root x. What was f second derivative at x is minus 1 by 4 x to the power 3 by 2. And f third derivative at x is 3 by 8 x to the power 5 by 2. Now this will imply infinity norm of third derivative. This is a decreasing function and magnitude is still remain the same only, and this will be attained maximum at the left hand point x equals to 1, that is equals to 3 by 8. Now if you use the quadratic interpolating polynomial piecewise structure, so what will be the maximum error is infinity is less than equals to, so norm of f third in infinity norm of this divide by 72 root 3 times h cube. So that is equals to 3 by 8 into 72, that is 256, right? 72, no, sorry. 576 times root 3 times h cube is 1 by n cube, and what we demand is less than 10 to the power minus 6. Right? Okay, so what will happen now is that is equals to, so this is if you 192. So this will implies this is only possible 1 by 192 root 3 times n cube must be less than 10 to the power minus 6. This is provided so n cube must be greater than 10 to the power 6 by 192 root 3. So here n equals to 20 will work. So there is a dramatical change, a drastic change you can say. Okay, so earlier n equals to 200 and now it is n equals to 20. Okay, so right. So this is about the piecewise quadratic interpolation. Okay, and here as I told you that you can retain the structure piecewise when you are targeting only one time differentiability, continuously one time differentiability. Okay, and let's say if you have the previous example, so let's say this is there, right? And I wish to work with the now define the corresponding this is quadratic interpolating polynomial piecewise with piecewise structure. So if I have with the same here data x f, so you have 1 2 3, and this is 1 1.414 1.713, right, 732. And you have first divided difference is 0.414, here 0.318. So here you require a second divided difference as well. Okay, so what it will be? So 0.318 minus 0.414. So that is equals to minus 0.096. Now you have, so for this here, you have only 3 points. So you can either, so you don't know the function, so you have to go with the single polynomial. So you can increase one more value here, right? You can increase one more value, 4, and let's say 5. So for square root is 2, and 5 square root is 2.23. Okay, so 2 minus 1.732, that is 0.268, and 0.23 minus 2 is 0.23, and what we have here is 0.268 minus 0.318, that is minus 0.05, and you have 0.23 minus 0.268, that is minus 0.038. So you require up to second order divided differences, right? Okay, so this is going for the continuity. You are going to take these two blocks here. So x0 to x1 is 1 to 3, and x1 to x2 is 3 to 5. So you have here x0 is 1, x1 is 3, and x2 is 5. So here your interval is 1 to 5, and h is equals to what? 3 minus 1, that is 2. H value is 2. Now, if you going with here two subintervals, so G2 restricted at x0 to x1 is equals to f at x0, then this, right, and then this. So this is equals to 1 plus first divided difference, that is 0.414 times x minus 1 plus, or this is minus 0.096 times x minus 1 into x minus 2. Now, similarly, G2 restricted on interval x1 to x2. So you are going to start with this. These three values you are going to use. So that is equals to 1.732 plus 0.268 times x minus 3 minus 0.038 times x minus 3 into x minus 4. Now you can verify that at x1, at x1 is equals to 3, at x equals to 3, so this is 0, this is 732. So at x equals to x1 equals to 3, this is 3 minus 2, this is 3 minus 1, this is 3 minus 1, and you keep all the things. So G2. So if I say this is P1 and P2, so what it will be here if I, so this value is 1.732. It's very clear. Yes, yes, right. Divided by 2 here. Divided by 2. Okay. Oh, I have created the forward difference table here. Yes. So divided by 2, and here is divided by 2. Yeah, fine. Yes. So now it's fine. 1 plus 0.828 minus 0.096. Yes. So that is going to be 1.7. Yes, right. Thank you. Right. So yes, so I have created a forward difference table here. Okay. So we have to create the divided difference table here. So for this here, so you have to divide by 3 minus 1 and 5 minus 3, right? So here for this case 3 minus 1, for this case it is 4 minus 2, and for this case here 5 minus 3.